And good morning. We start week 2. Now, I am interested in creating a logical argument that has perhaps multiple quantifiers. Now, there's a classic song, probably your parents were little. In fact, maybe it was your grandparents. It's everybody loves somebody sometime. Everybody needs somebody now. Now, the person who wrote that song clearly had studied discrete math because the whole song is about quantifiers, both existential and universal. So what I'd like to do is take some of the lyrics of this song and break it down into the quantifiers that are right there. So if we said, let's just take the first line. Everybody loves somebody sometime. Okay. Well, clearly there's a universal qualifier in there, and there's also an existential qualifier in there. In fact, there's 2 existential qualifiers. This is an extremely complicated statement mathematically. So we'd like to be able to look at this and pull it apart. So we're going to look at a particular type of logical argument. It's the multiple quantifier logical argument. Okay. And so sort of the general case. I'm trying to find my generic here. Hold on a second. Oh, here we go. If I have a situation as follows, for all x in the domain where x lives, okay, there exists a y, and I'm going to write a different set because it could be a different domain. Y could come from the same set, y could come from a different set, such that, and now we have a combined statement, P of x, y. Before we just said P of x, because, okay, go ahead and mute yourself, guys. Okay, so I have a situation here where I'm looking at input and output. Can please make sure you mute it. Got a lot of background noise here. So for all x in the domain where x lives, there's a y in the domain where y lives. These could be the same set. They don't have to be. Such that I have a truth of both of them. So that's exactly what I have going on here. So in this case, my set would involve people. Okay. So I would like to set this up, since my overall set is going to be people. Everybody comes from the set of people. Somebody comes from the set of people. And then there's a sometime would be a time thing. So how can I start this? Well, I think I need to start with this guy right here. How about there exists time t, or if you want to say it more formally, there exists t in an element of, let's say, the set time. We'll call that be the set. Okay, there exists a t, there exists a time. Okay, such that, now let's attack this part. Everybody, that would be all people. So how about for all x element of the set of people? And by the way, if you want to off to the side, you could just use a letter of the alphabet that would be people. I'm just going to be really from the set of people. Now help me out, folks. Everybody, for all x in the set of people. You want to help me out here? What do you think the next line would be? Everybody loves somebody.
Such that.
Not yet. We need the there exists before the such that. So how about for everybody? Think of yourself. Isn't there? There's someone for you. So there would have to exist for every person. This is for every person, for everybody.
Somebody they love.
So there exists
at least one person.
Well, so what would that
exists X?
How about there was, if you love yourself, I guess, God. Right? So let's say there exists right now there exists a Y. Now, does Y also come from the set of people?
Yes.
Yeah, Y is not coming from the set of dogs. I mean, you know, yes. Everybody has a dog they love, sure. So Y from the set of people. Now I do my such that. What? X loves
Y.
Now I could define, by the way, if you really want to get formal, which we will, I want to start with something. We could say this way, LXY means that X loves Y, not Y loves X, by the way. So we could define that. And we could say capital P is the set of people, not people. So then in that case, you could have X being an element of P and Y being an element of P. We could get really formal and do it this way. That's most textbooks would do that. I don't mind using some words here, but you said this is a very complicated statement. The reason it's complicated is because I have a universal and an existential qualifier in the same statement. In other words, I have something of this form. So this is the form I want to be able to translate. Most of the time when we've done stuff, we've only used one. Okay, there exists something such that, or for all things, this. But this one is involving both. Okay, so let's do a different one. I love this example because it's, it does exactly what we want it to do. Oh, hold on a minute. Well, that didn't come out well. Hang on just a second. I need to get something to clean that off there. Thanks. That doesn't happen very often. There we go. Be awful if I can't use my whole board here. Now we're going to do lots of examples of this type of reasoning today. So then the next one, what if I have something of the form that using the same two sets, the same two domains D and E, there exists X in D such that for all Y in E, the statement is true. How could we take that last song? We said, everybody loves somebody. Can we translate it if I use the same for the same thing, this would be love and all that. Everybody loves somebody. How could you translate this one then? There exists a person from the set of people such that. The original was everybody loves somebody. What would this one say?
Somebody loves everybody.
Perfect. This is saying somebody, there's a person out there who loves everybody. How do I know it's everybody? Because there is a person in the set of people such that for every other person, X loves that other person. There is somebody that loves everybody. Oh, okay, that makes perfect sense. So is it easy to write something like this? Yeah. So now I'm going to give you a simple example of a situation. We're going to use formal sets so we don't have to worry. Let's suppose at a particular place of business, let's call W is the set of, keep it simple, workers at a factory. Okay. And let's say that M is the set of music played on the radio. How's that? Okay, so you have music playing on the radio, you have people working at a factory. Now the people working in the factory are listening to the radio. Okay, so let's say, let me use really simple, let's see. And hold on, which way do I want to go here? All right, so we can say that, let's say L of little w, little m. I'm trying to make these capital little. L of little w, little m means that worker W listened to song little m on the radio. How's that? Okay, so this is our P of XY in a sense. Okay, I'm using worker, music, listened. Okay, so I'm giving you a really simple way of saying this. So if that were the case, how would I say there is somebody at my place of employment where I work? I work here. There's somebody at my place of employment who has listened to every song on the radio. I want to say that using the symbolic notation that we just went over. There's somebody at my place of work that has listened to every song.
There exists,
Okay, there exists.
X and W.
W,
Well, we're going to use these variables. So W, little w. Okay, so there
little w.
exists little w.
in domain of W.
Good. That's the easiest way of saying it. And look, there's a worker in the set of workers. And there's an individual worker in the set. Okay, perfect, perfect. Now, whenever there's a there exists, now it's there. This is where the such that.
Such that Y, no, sorry, M,
Well, how do I say they've listened to all songs?
For all M in
Right.
domain of capital M.
Perfect. Okay. I've got a worker in the set of workers such that every song, now finish it for me. And by the way, a comma would be appropriate here, not a such that. I'm just continuing my sentence. Such that what?
LWM,
Perfect. That's perfect. Except my writing is really not perfect here. L, little w, little m. I have just said there is a worker out there such that every song that can possibly play on the radio, that person has listened to that song. Perfect, perfect. Okay, so that was the first instruction. Now, the second instruction is going to be, there's this one song that just plays all the time, drives everybody crazy, but everybody knows this one song. There's a song out there that everybody has listened to. Now, there might be multiple songs, but there is a song out there that everybody has listened to. There's a song out there and everybody's listened to it. Now, let's do that one next. There's a song out there that everybody has listened to. Again, this is exactly the stuff we're talking about. Everybody loves somebody. It's the same kind of thing. There is a song, everybody's listened to it. Now you have to decide what order you want to go in. It's probably easier to start with the workers again.
You want me to start for this one?
Start.
So for all lowercase w in W, capital W, there exists a lowercase m in domain M, comma LW,
such that.
such that
Again, it's
LW.
more for an English thing. Okay, now what did we just say? For every single worker, there is a song. There's a song for every worker. There's a song that worker has listened to that song. That means there's a song that every worker has listened to. Could you start by saying there is this a song such that for all workers they've listened to it? Could you say it in that order? Sure.
So Professor, I actually have a question because that's what I wrote. I did there exists M in capital M such that for all W in W. And then I put L of M comma W.
Oh, okay.
Is that correct? Because
Yeah,
I switched the order.
The kind of it's like the XY. Before the first element
Okay.
has to come from the same set.
Okay, so it's always going to be that way.
Yeah, yeah. Because of how we defined it, the first one comes from the first set, second one comes from the second set.
That was the
So,
question. Perfect.
Yeah. So I'm still the question, is this valid? I think it is. Yeah, I think it is. But the order that we present, it probably makes more sense, this one, just because then the order of the variables
Right.
is the same. And by the way, Tom, you just pointed out why it might be better to do this for the possibility of somehow switching, because again, think input output. So the X's and Y's really can't trade places in that sense. Now, is this problem complicated? No, but what we're doing is we're doing multiple quantifiers. And then how would we say that? Now there's nothing about this that's overly complicated. I think we all agree. So of course, let's get to the next part, everybody's favorite. How do I negate a situation like this? Ooh. Now, let's go back to our everybody loves somebody. Everybody loves somebody. How would I negate that? In words, not symbols. Always, by the way, it's an absolute rule. Always think words before you go to symbols so it makes some sense. Everybody loves somebody. I want to negate that.
Would it be somebody doesn't love anybody?
Yeah, there is somebody. Like you said, at least one person. There's somebody who doesn't love anybody. And I think we all know who that person is, right? Everybody loves somebody. Everybody loves somebody. There's somebody out there. No, there's somebody out there that this fails for. They don't love anybody. So let's start with that one. But let's just start in words. So we said everybody loves somebody. There is a person who doesn't love anyone. Now, let's go with the symbolic because it might be easier now. So the first time it was for all x in D, there exists y in E such that P x y. In this case, P would be love. All right. So now my question is, how do I negate this? Now think about what you just said. And by the way, we talked about this last week. Remember, the negation of a for all involves a there exists, and the negation of a there exists involves a for all, but it's how we say it that's important. So I want to negate the for all. So let's see if we can do it symbolically now. So how about there is an x in D
Such that.
Professor, I have a question.
Yes.
It might be my English, but for me, this phrase doesn't look correct.
Which are you talking about, the second line?
Yeah, the negation, because for me, it sounds like there is a person that kind of hates everyone. Or
Well,
maybe
okay. You're saying if you don't love somebody, does that mean you hate them? In other words, would it be a safe statement to say you either love somebody or you do not love that person? Is that a safe statement? I've made it binary. There's only two. I love them or I don't love them. Not loving them doesn't necessarily mean I hate them. I just don't love them. I'll give you an example. Last night we had a really nice dinner and we had broccoli. I eat broccoli. I don't love broccoli. Oh, I really don't love broccoli. I don't hate broccoli, but I'd rather have something else. But I will eat my broccoli because it's good for you. Did you see what I mean? I don't hate it, but I certainly don't love it. There is an in between. So if love and hate were the only options, then saying they don't love would be the same as saying they hate. But not loving doesn't necessarily imply hate any more than my water bottle being full or my water bottle being empty are the only two options. No, full and not full is safer. So loving and not loving is safer because then it implies everything else. So you are correct if it's only love and hate as options. Does that help, Sergey?
No, I think my question was a little bit different. It's not about.
You said, doesn't this mean hate? Absolutely not.
No. My question is more about anyone and someone, something like that, because everybody loves somebody means that every person loves at least someone, right?
Exactly, at least one person.
Now, if you say there is a person who doesn't love anyone, well, maybe it's right. Okay.
Well, hold your thought. You know, and again, I love the fact that we're talking about something, you know, when we throw in the word not, remember the only time you can replace a not something is if it's binary, like on, off. You know, not true means false. And, you know, not one is zero when we're talking about computer language, right? The light switch is not on, it is off. But the glass of water not being full does not mean it's empty. Not loving someone doesn't necessarily mean hate. So you can be safe by saying not love. Here's the tricky part about the negation, okay? And again, I'm using the words because it's easy to go backwards and think. All right, there is a person out there such that I still want to say for all Y and E. Now, where's the negation coming from? Not.
Professor, actually, so why do you use a different set? Like, why is it if X and D and Y and E when X and Y are both people?
Because in general, everybody, how about everybody loves a particular kind of animal? How about that? Or everybody loves a particular kind of dessert. Everybody loves a particular football team. In other
Right.
words, the first is from the set of people, the second thing's from the set of things they love. Now, in this case,
Got it.
it just happened to, both sets happen to be people. But does the second set have to be people? Like I just say, it could be dogs, it could be football teams, it could be desserts. So there's no requirement that the second thing has to be the same kind of thing as the first thing. I said everybody loves somebody. That makes it easy. So in this case, the set of, in this example, E and D would be the same sets. But how about if I said everybody loves a dog?
Yep. Makes sense. Thank you.
Right, you say, well, my girlfriend.
So, right, but
No.
in this specific scenario, it could make sense to put them both under D, but in general, you want to put them, make sure.
Yeah,
that-
yeah.
Got it.
In the
Thank you.
previous example we just did, we did workers and we did music.
Yep.
They
Yeah, I
seem
just
to
want to
come
make
in the
sure.
same
that-
set. Does that make sense? Much safer to keep these as separate sets, and then relying on every dog loves another dog. Okay, that's great. Every dog loves a bone. Okay, a bone is
Sounds
not
good.
a dog. So,
Thank you.
all right, but now notice where the negation goes. So if in this case P represented love, so in this case P would mean X loves Y. So this statement would say it is not the case that X loves Y, which is equivalent to saying X does not love Y. That's what that says right here. X does not love Y, if I'm going that one. So when I'm negating this statement with the multiple qualifiers, the negation, you don't say there does not exist an X. You don't say it is not for all. You got to be careful. Because remember I said the negation of something is always true is there's a situation where it's not true. Oh, what's the same saying? There's a situation where it's false. Okay, so I don't say it's always false. There's a situation where it's false. If I said something is always true, the negation is there's at least one time when it's not the case where it's true. Something always happens. There's at least one time where it does not happen. See, in other words, does not happen doesn't mean something else took place. It just means this thing did not happen. So now let's go to, I'm not really sure here. Now let's go to the other type of multiple. Let's see. Put a line right here. Okay, the second one was there exists X and D. And I said, yeah, such that for all Y and E. Now, in terms of the everybody loves somebody. Everybody loves somebody. What does this say? If I'm using this.
There exists someone that loves
In
everyone.
English, you don't talk.
There,
that.
somebody loves everybody.
Somebody loves everybody. Yeah. Okay, everybody cool with that? This is everybody loves somebody, and that was the translation. This is somebody loves everybody. There's a person out there such that for every other person on planet Earth, this person loves that person. Somebody loves everybody. That's me. I'm that person. All right. Somebody loves everybody. I always like to do any type of logical connectives like in this to actually put words in there to just to help me interpret and conceptualize. And when I'm doing a negation, does it actually make sense? Like Sergey was just asking, and that's the important question. Does it actually make sense when I start messing around and moving things and negating things? So how do I negate this one? Somebody loves everybody. How do I say it? There's someone loves everybody. There's a person out there who loves everybody. Well, first of all, the negation is when you say, no, that's not the case. There isn't anybody that loves everybody. How do I say that one? That's a little bit trickier.
There's someone who doesn't love everyone.
Yeah, but see, if you're the person who doesn't love everyone, I could still be the person who loves everyone, in which case it would still be true.
It should be nobody, no? Something like that.
There, how about if I just said this? Okay. First of all, my football team always wins. The negation is my football team sometimes doesn't win. In other words, there may be a game out there that we lose. Okay. Now, my football team wins at least one game. What's the negation of that? It's a tricky one. What's the negation of my
They
football?
don't win any games.
I don't win any games. So now how do I say that? Oh, but wouldn't that be for all? For all games, we don't win. So for all people, again, being generic, for all X and D,
So is it everybody loves someone?
no, now this was somebody loves everybody, and I want to gate that. I don't think there's any person out there who loves everybody.
Oh, okay. That makes sense.
So how about for all people out there,
Nobody loves everyone.
nobody loves everyone. That's another way of saying it. Okay, there is a person such that there's a person out there who loves everybody. For all people, I don't think they love they for all people. What? Now, this one's tricky. You said there isn't a person out there who loves everybody.
There exists.
Now, how do you say that? There isn't a person out there.
For all.
There isn't a person out there who loves everybody. So for all people,
There isn't.
so
A
for all
negation.
people, they would not love. So how about for all people,
All. Why?
you could say it this way: for all people, there does not exist this such that P. This is one way of saying it. I like putting the negation on here, but there is this way. For all people, there does not exist. For all people, there does not exist a person. That's one way of saying it. Okay. How about again, this gets into the mathematics a little bit later. I called it the math of at least one. I know that's a kind of a lousy way of saying it. If I said something happens at least once, the negation is it does not happen at all. Agreed? The negation, it doesn't happen at all. So there is no person out there who loves everybody. We agree with that. We're not saying everybody doesn't like everybody. Now, I'm gonna leave this one for a moment because now we're gonna move on. Let me see, make sure my notes here. I've got a couple different examples I want to get through. So let's see. And we got the last one. Okay. Oh, okay. Now I wanted to do a mathematical one. Sorry, I was trying to remember. Now, the author tried to do a mathematical epsilon delta statement. When you read the textbook's wonderful. She kind of whiffed on this one. she tried to do something from calculus in this format, and it didn't quite work. So I don't care if you remember your calculus in detail, but one of the most important things. This is day 2 of Calc 1 when we introduced the epsilon delta notation. Oh, you guys remember that? So an epsilon delta proof, if I'm trying to prove that the limit as x approaches a of f of x equals some finite value L, I want to prove this using epsilon delta. And the way you prove this is you say, oops, sorry. I'm not going to ask you to prove an epsilon delta. I'd like to know, is there a way of saying it using this type of notation? It is. This is probably one of the best examples. The way you did the epsilon delta proof is you started by saying for all epsilon greater than 0, the absolute value of f of x minus L less than epsilon implies that x minus a is less than delta for some value of delta. This is how you did the epsilon delta proof. So how do I do this using that other notation? It's for every positive value of epsilon, there is a delta such that this statement is true. Okay, so an epsilon delta proof, the author tried to do this and it didn't come out very well. So we can say for all epsilon greater than 0, that would be the same as saying for all epsilon an element of the positive real numbers. There exists a delta also, by the way, from the delta has to be positive, it can't be 0, such that, that's the more formal way of saying it. Okay, and what we find is this delta ends up having to be a constant multiple, or at least a function of epsilon. That's what ends up being true. As scary as this was in Calc 1, you notice it's the exact same logic, exactly the same logic. And this also applies then when I'm trying to do things with sequences and series. I'm trying to make conclusions because they involve limits. I don't need you to remember the epsilon delta. This is the epsilon delta. This is what it says. But now that we understand the notation, okay, for every positive value I can possibly have, and we usually think of epsilon being small, not large, but it has to be positive. There's going to be a delta out there, and yada yada yada. I did that stuff, crazy stuff. All right, now next thing, can I make a universal statement in general? See, if I say, if you score over 90%, then you will get an A. I'm giving you a conditional statement. You scored over 90, you got an A, therefore the statement was valid by modus ponens. Okay, you did not get an A, therefore you did not score over 90%. That statement is valid by modus tollens. Okay, great. We've been working on that. Can I have universal statements for every situation? The following, okay. I'm going to leave the calculus realm. We're not going to do any more calculus. That's the only time I'm ever going to mention that. Don't worry. Some of you are getting cold chills and things like that. All right. So what if I have a statement of the form for all x, and again, probably should say for all x, I mean, in the domain, if this is true, then this is true. P and Q are just statements. Okay, for all x in the domain, if the first one is true, the second is true. So maybe my domain is the set of positive integers. Okay, and maybe P of x is some algebraic statement. X is bigger than a certain amount, and then Q would be some other algebraic statement. It doesn't really have to be an algebraic statement, but it just basically means if x makes P, if x, for any value of x that makes P true, x will also make Q true, period. Okay, that's it. That's what it means. This is called the universal modus ponens, because I'm saying not for one situation, I'm saying for every situation that occurs. Every conceivable situation that something happens, this would be true. So an example would be, and this is something we're going to be starting, I think, let me real, is it next day or the day after? Sorry, I lose track. I think it might be Wednesday's lecture. We're going to look at properties of integers and things like that. Now, if I ask you to add 2 integers, we know the result is an integer. That's not really the point. Now, I want you to think of something that we're going to prove later. But if I took something like an odd integer and I raised it to any integer exponent, positive integer exponent, for example, I took 3 and I cubed it, I raised it to the 4th, I raised it to the 5th, whatever, positive integer exponent. If I took an odd number and raised it to a positive integer exponent, would my result be odd or even? Now think about that.
Even.
An odd integer raised to a power.
Oh, odd.
Yeah.
Sorry.
Yeah. If I took an even integer and I raised to a
Even.
Again, my powers being positive integer exponents. 2 to a power, 4 to a power, 6 to a power? What do you think?
Even.
Yeah, that's, by the way, that's something we will prove, by the way, but it's actually a very powerful statement. So if I just said, if an integer is odd, then how about this? Its cube is odd. Do you believe that statement is true?
Yes.
Okay, so now I'm going to pull an integer out of a hat. K equals 5, therefore k cubed is, oops. You agree that this is a true statement? Does this follow? K equals 5, therefore k cubed is odd. Does this follow from this statement right here? Is it yes or no? Anybody? If an integer is odd, then its cube is odd. K is 5. K cubed is odd.
Checks out.
Yeah, it's true. This is true. Why? Because we just said if an integer is odd, I gave you an odd integer. I didn't say all odd integers. I gave you a very specific odd integer. Oh, I gave you an example, in other words. Oh, okay. Okay. So this says for every x in the domain. So what if you pick out a particular x in the domain? Call it whatever you want. But if I pick out a particular x in the domain, which I just did, I picked a value, call it 5, then that's true. This would be the universal modus ponens example. Okay. How do I get modus tollens? Let me go. This is called universal modus ponens. You know, P implies Q. We already know that. For all x in D, if not Q, then not P. Is this saying exactly the same thing?
Yes.
Yes.
It is.
Yes.
Because the form, this is saying essentially P, if then, P implies Q. This is saying not Q implies not P, which is called the contrapositive. So if this is universal modus ponens, then this is universal modus tollens. Remember, that's the only difference between the two. They're both valid ways of making conclusions, but one is in a negative way. So how can I do that here?
If an integer's cube,
Let me just start with that. K cubed is even.
k is even.
K is even. Or let me just start, K is even, which basically means in this sense, it's not a,
Right.
By the way, say even because it's odd or even, that's binary. But, oh, okay. So if the cube of an integer is not odd, meaning it's even, then the integer itself must be even. And by the way, we're going to prove things like that. These are actual things that require proof. You can't just say it. But right now we're just saying it because we're trying to do the logic part, not the actual calculation part. So this would be an example of universal modus tollens, which again, it's not complicated, but it's said in the reverse. So anytime we're saying all, and we don't always say that. So if I said to you, all discrete math students are brilliant. All discrete math students are brilliant. Biff is a discrete math student. Can you conclude that Biff is brilliant?
Yes.
Yes. Okay. No discrete math students eat broccoli. No discrete math students eat broccoli. Skippy eats broccoli. Therefore,
He's not a discrete math student.
Skippy's not a discrete math student. Would that be true also? Yeah, that would be
Yes.
universal modus tollens because we would in reverse. Those are never meant to be tricky. It's the whole inverse converse error kind of thing. But if we make an absolute That's what a for all is. It's an absolute mathematical statement. We like absolute mathematical statements, but we can't always make them. But we always have to make the correct conclusion if we make that statement. Okay, so let me keep going here. Make sure I'm not leaving anything out. Okay. Oh, and now major thing. Now I'm going to introduce a term that we're really not going to dwell on until much later. Later in the course, we're going to talk about what are called the equivalence relations and terms that you may have heard: reflexive, symmetric, transitive. We're going to talk about these and their properties. This is much further in the future, but there is one that applies across the board in mathematics. Let me give you a really simple algebraic example. Okay, 4x plus e to the 3x squared 10x equals, I don't know, 7. E to the 3x squared 10x equals 3. What does x equal?
1.
1. How, that's so complicated. How'd you get 1? What did you just do? I hope.
7 minus 4x.
Well, you replaced this quantity here with this quantity here. That's what I would hope you did. I'm hoping everyone looks like, oh yeah,
Same thing.
that looks terrifying. But you just replaced this with this. How come you can do that? Oh, we all, by the way, everybody alive, I would hope, would do that. How come you can do that? What justifies that step? Is it possible that it's not valid? Now, you just employed substitution. I mean, that's from remedial algebra, right? If two things are equal, I can replace one with the other. Why? This is what is called, this is what is called transitivity. Now, this is transitivity of equal sign. And in the simplest case, now this is something that I love doing problems like that, because at first it looks scary and then you realize it's real easy. Okay, transitivity. If A equals B and B equals C, then what must be true? We just did this. If A equals B and B equals C, then
A equals C.
A equals C. I mean, we're very familiar with it. This is how you do substitution. This is the only part of algebra that is truly abstract, is the concept of transitivity. A equals B, B equals C, then A equals C. Now I can do this. I could say A equals B, B equals C, C equals D, and on and on and on. Now, transitivity has many uses. It's not just the equal sign. It also is true in inequalities. Oh, if A is bigger than B and B is bigger than C, then A is bigger than C. I can apply this in many situations. If the line A is parallel to the line B, and they're distinct lines, and the line B is parallel to the line C, then the line A is parallel to the line C. Transitivity applies for many types of things. It applies to congruence in geometry. But for right now, we just want to keep it really simple. Transitivity is a fairly simple notion. Now, what about this? If P, then Q. If Q, then R. If P, then R. I'm putting question marks in. What do you think?
Yeah.
If we score more points, then we win the game. If we win the game, then we get the trophy. If we get the trophy, there will be a citywide celebration. If we score more points, there will be a citywide celebration. Yeah. Transitivity applies particularly to implications. That's one of its more important uses. Oh, so P implies Q, Q implies R, oops, therefore P implies R. This is true. And by the way, this is easily represented with a true, sorry, I just said Q again. Sorry. This can easily be shown with the truth table, and I'll leave that up to you. But the transitivity of implication is a very powerful tool, because the first thing happened guarantees the second thing, and the second thing guarantees the third thing, and the first thing guaranteed the third thing. I can always do that. And as a result, I can make conclusions. Okay. So I want to do a really simple example of this. It's kind of fun. There's a problem in the text. If you have your text, it's easier. I'll write it down. Otherwise, it does take a little while. And it's the concept. It's kind of a puzzle. Now, I don't know if you guys have ever done certain types of puzzles, but there's a lot of types of puzzles out there that are word puzzles. And it might be, one of the clues might be, if it's blue, then, it's the following. And another clue might be if it's red, then something else is true. And I don't have a blue object here, therefore, and I can make all these conclusions based on weird statements that I'm putting all together. I remember doing these things when I was younger, and people couldn't figure how do you come up with that conclusion? Well, I'm just using all the information and kind of filling in the holes. So it starts like this. The first line is, I'll read it out to you. If you have your book, that's even better. It's problem 31. I trust every animal that belongs to me. I trust every animal that belongs to me. Now, the second statement, this is going to be kind of tricky to get all of them in here. Second statement is dogs gnaw bones. The third statement, hold on. I admit no animal into my study. I admit no animal into my study. Hold on. Unless they will beg when told to do so. Unless they will beg when told to do so. This is a long one. Fourth, all animals in the yard are mine. Fifth, there's going to be two more lines, so you don't need to write these down. You can just follow along and look later. I admit every animal that I trust into my study. Into my study. Oh, good, I got that one in there. And the sixth and final statement before the conclusion is the only animals that are really willing to beg when told to do so are dogs. The only animals that will beg when told to do so are dogs. Now, the conclusion is, therefore, all the animals in the yard gnaw bones. Therefore, all the animals in the yard gnaw bones. All right. I would like to put these together in a logical order where each one implies the next one, starting with the first. And there are 6 statements altogether. Oh, by the way, they're definitely not in this order. Now, we have one major problem here. I just talked about the transitivity of implications. Oh, so if I have 6 implications, let's say A, B, C, D, E, F. If A implies B, then B implies D, so on, so on. E implies F. Then is it correct to say A implies F? Yes, it is. Oh, okay. So if I have 6 implications that hopefully one leaves off where the other one begins, I can clearly do this. Great. Except the problem is, how many implications did I just say? How many of these did I say as implications, by the way? How about none? I didn't make any of these into implications. So the first thing we need to do is make each of these into an implication in order to be able to link them. So how do I make them into implications? For example, dogs gnaw bones. How do you make that into an implication? Anybody? Keep it simple.
If the animal is dog, it will gnaw bones.
That's
Then
it. Perfect. Let's if an animal is a dog, then it gnaws bones. Well, no bones. Oh, okay. I started with the easiest one. How about all animals in the yard are mine? Is that an easy one?
If an animal is in the yard,
animal is in the yard,
then it is mine.
and it is mine. I might not be able to finish all of these just from a space standpoint. Okay, I'm taking the easy ones. All right, I trust every animal that belongs to me. I trust every animal that belongs to me.
If an animal belongs to me, then I trust it.
Perfect. If an animal belongs to me, then I trust it. I probably picked the longest example I could think of, but that's okay. I admit no animal into my study unless they will beg when told to do so.
If an animal will beg when told to do so, I will admit it into my study.
Good, because this one is in kind of in reverse. So if an animal will beg, I'm going to put ... admit into my study. I'm going to do that because it's a little bit long. Into my study. Perfect. We're almost there. I admit every animal that I trust into my study. Is it if I admit, then I trust it, or if I trust it, then I admit it? That does matter.
If I trust.
I admit every animal that I trust. So if I trust it, by the way, do I potentially admit animals that I don't trust as well? Sure. But the ones that I trust, I definitely let in. So if I trust it, okay, then admit. How's that? And what's the, oh boy, this is gonna be a tricky one. The only animals that will beg when told to do so are dogs.
If an animal is a dog, then it will beg.
If dog, then beg. Okay. Sorry about that. So all animals in the yard gnaw bones. If an animal's in the yard, then it will gnaw bones. Now, what does that mean to you then? So here's an easy way to do this. The way I like doing this is not necessarily, putting them all in order. Is there an obvious first or last? All animals in the yard gnaw bones. If an animal's in the yard, then it gnaws bones. We all agree with that one.
Yes.
Which is clearly the last one.
2.
2, because that's the only one that concludes that it gnaws bones. So this is my logic. I'm going to put, what color did I not use? So A, B, C, D, E, F. Okay, so this would be F. Okay. If an animal is a dog, then it will gnaw bones. Are there any that conclude, if an animal belongs to me, then I trust it. If an animal will beg, then I'll admit in my study. If an animal is in the yard, then it is mine. If I trust the animal, then I admit it. If the animal's a dog, then it will beg. So do you see, is there an obvious first one? Maybe that's either one. Is there an obvious first one? So I got
number 4.
All of these things are happening in my yard. Agreed? So the first one
is 4.
If an animal's in the yard, then it is mine. Okay, so I got to start somewhere. So that would be the first one. Okay. If an animal's in the yard, then it is mine. Now let's continue. Then where would that lead me next? I now have an animal. So the animal now belongs to me. So which one involves that?
Number
First
one.
one.
First one is if an animal belongs to me, then I trust it. So it belongs to me or it's mine. And now if it's mine, then I trust it. So that would be my B. So we're halfway home. Okay. Now, which one picks up from if I trust it?
5.
5, if I trust it, then I admit it. You guys kind of getting the hang of this. All right. Now, where does that go from there?
Is it number 3?
Yeah. And then see where we see, hold on, A, B, C, that would be D.
But we have to switch it. Don't we?
Okay, I admit an animal into my study. I admit no animal into my study unless it belongs to me. I guess we could say if I admit it, then it belongs to me. Because that's kind of an if and only if, isn't it?
Mm-hmm.
So yeah, you're right. I probably could have wrote that in reverse order. Does that leave anything left? Excuse me.
6.
And that would be, what's that, E? Now, this is kind of silly in a sense. You're going, why would I do all this? Well, the point being, I gave you 6, I don't want to say random statements because there was all interconnected. You know, I have a study, I have animals, I have dogs, I have trust issues with my animals. I don't know. But if we rewrote them as if-thens, as proper conditional statements, I actually can connect them and make conclusions. Now, I'm not saying this is how it works in a court of law. I got a guilty conviction because I was able to connect all of the dots. But in a sense, we're just doing logic and logical connectives. If A, then B, and then the next thing is if B, then C. Hey, I can say if A, then C, then. That I can be absolutely certain of. So there are certain things I can do. Excuse me. Let's see, is there anything else I want to get in this today? Yeah, I think that's pretty much where we want to get. Now, we've been doing things that are fairly, I mean, I don't want to say high level, low level, but there's no complexity in the stuff we've been doing. Simple truth tables, simple logic statements, lots of negations, things like that. Starting next day, next day we start the next chapter, chapter 4, and we actually start formal proofs. That scares the heck out of some people, but we're starting very, very low level and working our way up. And a lot of the stuff we're going to do is stuff you may have seen in a lower level course. For example, we're going to do at some point induction proofs, which most of you hopefully did in a pre-calculus course. You know, it's just not that complicated, but we're going to look at different types of proofs as we go on. And it will be things that you actually do believe. There'll be mathematical statements involving integers or rational numbers or things like that. What kind of conclusions? For example, the proof might be that the sum of 2 rational numbers is always another rational number. Yeah, that seems to make sense. Or the product of 2 rational numbers, or something about irrational numbers. We're going to then get into what are called the rules of divisibility, and which are actually kind of fun rules. Now, in chapter 4, this is the chapter where the sections are not in the same order from the 4th to the 5th edition. So I'm going to make it very clear when we get there. I'm not sure exactly where it switched. I can't remember. I have to pull out my old 4th, but somewhere in the middle of chapter 4, the sections were renumbered. So if you're using the online free 4th edition, we're going to have to make sure you go to the right section. So rather than worry about section numbers, I'll tell you what the titles of the sections are. Then it'll be easier, because the sections themselves are absolutely the same from each book. Just the numbering of the sections might be slightly different. Okay, so the content and the problems are the same. All right, so I'm going to stop there.